Thank you. Thanks for the introduction, and thank you very much for the invitation to speak here. My traveling schedule's been somewhat curtailed by the pandemic, which is to say I haven't been out of the state in a year and a half, so it's nice to be able to go to a conference again. So let me just start with some conventions before I start talking about math. We're going to talk about arbitrary, complete, non-Archimedean fields, but just so I don't go crazy, I'm going to assume that the evaluation is non-trivial. We use this is the notation for ring of integers and residue field. I'll talk about analytic spaces in the sense of Berkovich. And so I'm going to, when I say curve, I'm going to mean a compact, rig, smooth curve. So again, this is mostly for simplicity. Everything I'm going to say will also work for non-compact curves, but let's just talk about compact ones for the moment. Should work for non-compact curves. It's not written down. And I want to just mention that I'm going to talk a couple of times about formal models, but really just of curves. And that's a formal integral model over the ring of integers. Oh, yeah, and the one reason I wanted to say that is because there's a notation for its special fiber. You put an S in the subscript. Okay. So back in 2012, Chambert-Loir and Ducros introduced sheafs of smooth real-valued differential forms on Berkovich spaces in a very general setting. And that works on essentially any analytic space. And so these are supposed to play the role of the sheaves of holomorphic forms or smooth forms on a complex analytic space, and which forms a bigraded sheaf of differential algebras with respect to del and del bar. And so in this case, it's again a bigraded sheaf, but instead of del and del bar, we have d prime and d double prime. I should say, by the way, that Walter Gubler will talk in much more detail about this when he gives his talk a little bit later on. This is just a basic, very one slide introduction. So they satisfy many nice properties. They have partitions of unity. There's a nice integration theorem, Stokes the formula, Poincaré the long formula, and many of the sort of basic properties you would expect from sheaves of smooth forms on an analytic space. And in particular, you get Dolbeault cohomology groups. So by the way, I'm using the subscript SM to stand for smooth, and you'll see in a minute why I'm making that distinction. All right, so, and for me also, the Dolbeault cohomology groups will all be with respect to d double prime. There's an involution that switches d prime and d double prime, so it's that you just choose one and then stick with it. It doesn't really matter. Okay, so then once you have this definition in place, you can ask the question, for instance, what is the Hodge diamond of a smooth curve with respect to these constructions? So in his thesis, Philip Yell studied this question, and he proved in particular that, so again, for simplicity, you assume K is algebraically closed with residue field equal to complex numbers. If you have a smooth projective curve that is not a Mumford curve, then H11 is infinite dimensional. Which may not be what you expected. So why is this true? What happened to make it infinite dimensional instead of one dimensional? So in the Antoine's theory, harmonic functions on curves are not smooth functions. So by harmonic, I mean in the sense of Chuyer's thesis. So it's some sum of outgoing slopes equals 0 condition. And smooth is in the sense of Chambert-Loir and Ducros. One of the things, when you've defined a sheaf of smooth differential forms, you in particular get a notion of smooth functions. It's the 0,0 graded piece. And so I should just say that what Philip did was, in what sense is this, quote, the thing that went wrong? Well, what Philip did was he showed that the infinite dimensional piece, essentially, of H11 exactly comes from the quotient of the sheaf of smooth functions by the sheaf of harmonic functions. It's some quotient, this is some skyscraper sheaf, which is infinite dimensional as a real vector space. So in in Walter's talk, Walter will talk about some work that we've been doing over the past year or so, where we set up a theory of smooth real-valued forms analogous to the Antoine's theory, in which harmonic functions are by definition smooth. And this is also set up in essentially the same generality as Chambert-Loir and Ducros are working, and requires a bit of work to actually make everything go through. But yeah, I mean, you should think of that as very analogous to what they did. So then, as a sanity check, the first thing, right. We call these weakly smooth forms, and so the notation is just A upper PQ. So I reserve the subscript SM for the smooth forms in the sense of the Antoines. Okay. So this again is probably all very abstract, especially if you haven't read the Antoine's paper. So for the purposes of this talk, I can give you an alternative construction of the weakly smooth forms on a curve. And essentially, they all arise by pulling back from the skeleton. And this gives you a way to actually compute Dolbeault cohomology of curves, at least. So I should say maybe the goal here, or the goal of this particular paper, is to work out the theory and completely explicitly in dimension, work out the general theory that Walter and Philip and I set up in the first paper. And then in this paper, it's to work it out completely explicitly in this case of curves to see that you at least end up with the cohomological properties that you would expect.
So when you say pulling back from the skeleton, do you mean all kinds of different skeletons or just the minimal one?
I'm going to mean all kinds of different ones, but I'll make a precise statement later on. Okay, so first of all, I mean, in order to pull back a form from a skeleton, what is a skeleton? Well, it's a metric graph. So, which for me, it means a graph with edge parameterizations, like specific parameterizations of each edge with a closed interval, 0 to L of E. So L of E, of course, is the length of the edge. And I'm also going to work with graphs with boundary, and a boundary of sigma is just a finite set of vertices. I'm calling all my graphs sigma because they will arise as skeletons on the next slide. All right, so then the interior is the complemented boundary, as you might expect. So that's my notation for skeletons of curves. I'm going to need to use this parameterization of the edge, so I wanted to introduce the T sub E. So when I talk about skeletons of curves, I just mean in the sense of Chuyer's thesis from 2010, something like that. So if you have a K curve with a semi-stable model X, then you get a canonical metric graph with boundary contained in it. And if you like, you can think of X as just being a projective algebraic curve, and the formal model then is just the same thing as just a semi-stable algebraic model of X. In any case, you get a canonical metric graph with boundary and a deformation retraction onto that metric graph. So this is called a skeleton of X. So this way this works is the vertices of the skeleton correspond to the irreducible components of the special fiber. And in fact, more explicitly, there's a unique point of X that reduces under the reduction map to to the generic point of any given irreducible component, and that is the actual vertex as if you consider sigma X as being embedded inside of X. The edges correspond to nodal points, and the length of an edge corresponds to the local structure of that node. So what it means to be a node is that in an atol neighborhood of the node, X looks like a formal annulus. Formal spectrum of K circle, join XY, mod XY minus var pi. And the length of the edge is just the valuation of var pi. And now the boundary of the skeleton is just the same as the boundary of X. in the sense of Berkovich. So Berkovich defines very generally what the boundary of an analytic space is. And for curves, it's something relatively concrete. These are exactly the points of the curve whose corresponding irreducible components on the special fiber are not proper. And I should say that if the nodes are not rational over k tilde, over the residue field, then you also need edge weights. And so that's kind of an annoying piece of bookkeeping that you have to do that doesn't affect the theory in any meaningful way. So I'm just going to ignore them for the purposes of this talk. Okay. So the way this is going to work is that we're going to compute Dolbeault cohomology groups of graphs, and then we're going to show that when you pull back forms from graphs to curves, or from skeletons to curves, then you get the Dolbeault cohomology groups of the curves. However, I think it's not entirely obvious what smooth TQ forms on graphs are supposed to be. It took us a little while to come up with the correct definition, so let me tell you what that is. So a smooth function, first of all, is a continuous function that satisfies. Oh, and by the way, so that for simplicity, let's remove all valence to interior vertices, and you'll see why in a second. So the function is smooth on every edge, which means that with respect, if you compose with the parameterization of the edge, then you get a smooth function, and it's got to be smooth on one side at the vertices. Now, this is the reason I removed the valence 2 vertices, because otherwise you have to say that all of the partial at a valence 2 vertex, all the partial derivatives on both sides match up so that they glue together to make a smooth function. But again, that's kind of annoying to say that. All right, so what does it mean to be smooth at a vertex of valence at least 3? It means the sum of the outgoing slopes at that vertex is equal to 0. The outgoing just first derivatives. And it's smooth at a leaf vertex. That means it's going to be constant in a neighborhood of the vertex. An interior leaf vertex, rather. And there are no conditions at any boundary vertex. They can be whatever you want. All right, so you get an algebra of functions, which I call A00 of sigma relative to its boundary. So by the way, if you're wondering why it has to be constant in the neighborhood of an interior leaf vertex, so if we fast forwarded a bit in the talk, these things all arise by pulling back Lagerberg forms under harmonic maps from a curve to a Euclidean space, to R to the n. And any harmonic function is 0 in the neighborhood of a leaf vertex. So that's sort of forced on you by something I'll say later. Okay, so what is a 1-0 form? This is something, it's still very concrete. It is a collection f sub e d prime t sub e over all edges e, where, so you get a smooth function on every edge. D prime t sub e is just some formal symbol that reminds you how things are supposed to happen. So the function associated to the same edge with the opposite orientation is just the negative of f sub e. And the way you should think about this is, so how do you parameterize the same edge with the opposite orientation? It's like t sub e bar is t sub e of the length, t sub e bar of x is t sub e of the length of e minus x. So when you take derivatives, you're supposed to get a -1. So that's the reason it's supposed to, anyway, that's how I think about it. And okay, now if you have a vertex of valence at least 2, at least 3, this should be strictly greater than 2. I'll correct that in the slides. Now the sum of the values of these f sub e's at that vertex has to be equal to 0. And it's got to be 0 in the neighborhood of an interior leaf vertex. And again, there's no conditions at boundary vertices at all. So again, these conditions are kind of forced on you oh, sorry. So first I should say, if you multiply a smooth form by a smooth function, you get another smooth form. And these conditions are sort of forced on you because you want the derivative of a smooth function to be a smooth form. So if a smooth function, if the sum of the outgoing slopes of the function is 0 and you take the derivative, you're going to get something where the sum of the outgoing values is equal to 0. And if it's constant in the neighborhood of an interior leaf vertex, then its derivative will be 0 in the neighborhood of an interior leaf vertex. Likewise, you can define 0, 1 forms, and the only difference is you replace d prime by d double prime. Okay, so what's a smooth 1, 1 form? Looks like I got an extra pair of parentheses here, but now it's the collection f sub e, d prime, t sub e, d double prime, t sub e, where f e, so again, you have a smooth function on every edge. But now it's if the f sub e bar is equal to f sub e, because when you replace, again, d prime t sub e bar is the negative of d prime t sub e. The derivative of the parameterization of the opposite edge is negative the derivative of the parameterization of the edge, but you're multiplying by both of them. It's the same for d double prime. Again, it's 0 in the neighborhood of a leaf vertex, and there's no conditions on vertices of valency at least 3 at all. Or at, and again, also not at boundary vertices. So again, this forms a module over the space of smooth functions. And these conditions are defined, are forced on you by the fact that you want the derivative of a 1, 0 form, or I guess the d prime derivative of 0, 1 form to be a 1, 1 form. But notice, there were no, the sum of the values of a 1, 1 form at a vertex being 0 doesn't impose any conditions at all on its derivatives and the values of its derivatives around a vertex. So this is the reason why there's no conditions at vertices of valency at least 3. All right, and likewise for d double prime, there's a sign that you have to throw in so that the signs work out, but anyway, well, it's just a negative sign. All right, so now you can define wedge products of 1, 0 forms and 0, 1 forms in the way that you expect. And so when you put these all together, you get a bigraded differential algebra of smooth forms on a graph. And if you care, you can make this a sheaf of algebras on your graph. But we're not really, that's not going to be important for this talk either. Okay. So I hope that you'll agree that these are very concrete things. There's essentially smooth functions on edges with some mild compatibility conditions at vertices. We also get an integration theory. Oh yes, smooth means, Dimitri asks what smooth means. Yeah, smooth, so a smooth function from closed interval to the real numbers, but it just means C infinity function. That's right. A C infinity function from a closed interval to the real numbers, and it's got to be smooth on one side at the boundary, at the vertices. Okay, you integrate 1, 1 forms in the obvious way. You just sum over the edges, and then you integrate over every edge. Here, I guess I'm summing over unoriented edges. Boundary integrals are easy. That's the integral of the boundary of a 1, 0 form. I just sum over all vertices in the boundary and then sum over all outgoing edges of the value of f sub e at that vertex. Notice this is the same as the sum over all vertices because the second summation was required to be 0 at interior vertices. Likewise for A01, and we have Stokes' theorem. So the integral over sigma of d prime omega is the integral over the boundary of sigma of omega. So in particular, if sigma has no boundary, then the integral of an exact form is 0. Okay. So we get Dolbeault cohomology groups of graphs in exactly the same way. It's the kernel of D double prime divided by the image of D double prime. We could take cohomology with respect to D prime as well if you wanted, but you would get the same thing. All right, so as usual, I'm going to let little HPQ be the dimension of big HPQ. And G is just going to be the first Betti number of sigma. So the genus of sigma, if you like, it's the number of vertices minus the number of edges plus 1. Or maybe it's the other way around. No, that's right. Vertices minus edges plus 1. Okay, so the Hodge diamond of sigma delta sigma is, first of all, if the boundary is 0, it's exactly what you would think it is. H11 is 1, H00 is 1, and H10 and H01 are both G. And if the boundary is not 0, so I'm not sure what you would necessarily expect here, since, I mean, in the complex analytic world, these things would generally be infinite dimensional, I guess. But anyway, I guess I don't know how you would even define these in the complex analytic world, but this is what it is for graphs. H11 is 0, H00 is 1 still, H01 is G, but H10 is G plus the number of boundary vertices minus 1. And proving this is just an exercise in elementary graph combinatorics. It's really not, I mean, it's kind of fun. You know, you use incidence matrices and various properties of incidence matrices and fun stuff like that. Okay. So all of that is maybe the first 10 pages of the paper, or 15. Where it gets more tricky is now trying to relate this to the non-Archimedean world. So if you start with a curve, and remember, my curves are always smooth and they're rigged smooth and compact, and a skeleton associated to some semi-stable model. And there's, in particular, there's a retraction onto the skeleton. And so we define a natural pullback map from the PQ forms of sigma rel del sigma to the PQ forms on X. Now, again, these are the weakly smooth PQ forms in the sense of my paper with Walter and Philip, which Walter will talk about later. And it's a very, so it's natural in the sense that it respects integration, it respects morphisms of curves and harmonic morphisms of graphs, etc. So there's actually quite a lot of work that goes into sort of understanding, I mean, there's a lot of sort of combinatorial works that goes into understanding the behavior of smooth forms with respect to harmonic morphisms of graphs, which I'm going to completely gloss over all that. Although it looks like I would have had plenty of time to do it. Now that I'm looking at the clock. Okay, so the way to do this, I mean, the main idea behind this is you have to show that smooth forms on graphs are locally pulled back from Lagerberg forms under harmonic map to R to the n. So a harmonic map is just a tuple of smooth piecewise linear functions. And then you also have to show that if you compose retraction to the skeleton with a harmonic map to R to the real numbers, then that is a harmonic function on X in the sense of Chie. And so this is something that, I mean, is not, well, it's something that has to be proved. So yeah, actually, let me maybe say some more about that since I have the time to do so. Here we go. So, I mean, essentially what a weakly smooth form on a curve, by definition, is given by what we call a harmonic moment map. So this is H from X to R to the N. H is just a tuple, H1 through Hn. And Hi is harmonic in the sense of Touye. So we have a more general, we have a general definition of what it means to be harmonic that works for any analytic space, but for a rigged smooth curve, this essentially means it's piecewise linear and the sum of its outgoing slopes at any vertex is equal to 0, or at any point of the curve is equal to 0. So if you have a logarithm form, and a logarithm forms are essentially smooth forms, tensor, wedge, I guess P of Zn tensor wedge Q of Zn. So it's just some formal sum of a smooth form, some formal sum F I J dx d prime x wedge d double prime x, where this x is I guess a p tuple and this is a q tuple. Maybe these subscripts don't make sense. How about that? So by definition, a weakly smooth form it locally has the form h star of omega, which is just defined to be the pair of h and omega up to some sort of equivalence relation. When are two forms the same? So if you have, so in order to show that a weakly smooth form, so that the pullback from this, in order to define pullback from the skeleton, I have to say, what is your h and omega? And it's not so hard. So if you have a weakly smooth form on the skeleton, so the first thing you have to show is that locally there is a harmonic function, or a tuple of harmonic functions from sigma to r to the n such that omega is the pullback, and a logarithm form on r to the n such that omega is the pullback of eta. So this amounts to showing essentially that, so for instance, for smooth functions, this amounts to showing that if you have an embedded graph inside of r to the n, and you have a smooth function on this graph in the sense that I told you before, then it actually extends. So here, fe1, fe2, or I guess, okay. You have a smooth function to r, which is smooth. In my sense, that in the sense of what I was telling you before, then it extends to a smooth function on r to the n. So I wrote this down and I was like, well, geez, that sounds like an analyst might know how to do that. So I emailed our local analyst at Duke, Robert Bryant, and he, the next day he sent me back a nice argument, which shows you how to do it. So our analyst came through, this is possible. And you have to do some similar trick for 1, 0 and 0, 1 forms and 1, 1 forms, and it all works out.
Joe, for graphs, don't you locally around each vertex, so to say, have sort of a preferred embedding with respect to which you can define harmonic functions? Like the one you drew here for a vertex of valence 3, for example, namely just as a tropical linear space.
Well, the graphs we're considering just abstract metric graphs, and so there's no.
You have. Around each vertex, there's sort of a preferred way of embedding it into a. If it has valence n, you embed into an Rn minus 1. Just as like this.
Yes, yes, you're right. That's exactly right. So the way you construct these things.
That's the one you could always use.
Yes, that is. Well, that's the one that we use. That's right.
Okay, so you could might as well have defined it with that. Is that maybe the gist of it, or? Yeah,
we could have. That's right. But then it would be. One way to think about it is that the smooth forms and weakly smooth forms on an analytic space are defined entirely in terms of pullbacks from tropicalizations, because there's no. The skeletal theory in general is just not rich enough to be able to define things intrinsically. But in the case of curves, that it is the skeletal theory. We know enough about skeletons that you can define smooth things intrinsically to the curve, and then a posteriori relate smooth functions to the pullbacks of smooth functions under embeddings into Euclidean space.
Okay, good. Thanks.
And that's what's happening here. But yes, you're exactly right. You just you embed it as like the unit vectors, and then the -1 vector in r to the n minus 1, and then you have a smooth function on that thing, and you can extend it to all of r to the n minus 1, using that kind of trick. Okay, so that's step one, and then the other proposition that you have to show is that if or again, what I just had before, you have your curve, you have retraction onto a skeleton, and then you have a harmonic function r, and this composition, this is harmonic in the sense of Touillet, or the sense that Walter will tell you about later. And then the way you define the pullback, tau star of a form is just tau composed with, H composed with tau star of the Lagerberg form that you use to pull back to get tau, at least locally. Okay. So that's how pullbacks from the skeleton are defined. So one of the first things we prove is that all forms, all weakly smooth forms, I should say, arise in this way. So if I have a weakly smooth form on X, then at least after taking a finite Galois extension, there exists a semi-stable model and a form on the associated skeleton such that the form you started with is the pullback. So this is, in some sense, is mostly formal. It's just a question about gluing models. Yeah, I don't want to say more about that. You have a bunch of models on on a G cover of a curve, and you have to find some semi-stable model that dominates all of them simultaneously. But it's an argument along those lines. Okay, so there's two theorems here about Dolbeault, actually computing the Dolbeault cohomology of curves. So first, suppose X has a semi-stable model, and then we have to suppose that the skeleton has no isolated vertices, or really no isolated interior vertices. So the reason for this is if you have a proper curve with good reduction, if you have a proper curve with good reduction, then the graph is just the skeleton is just a point, and so it's got no Dolbeault cohomology at all, and so A11 is not going to be the correct thing. You're going to get 0 instead of 1 for A11. That's really the only difference. Then, but of course, you can always arrange for this not to happen by blowing up. You can take a blow up on your special. If you have an isolated vertex that corresponds to smooth connected component on the special fiber of your semi-stable model, and if you're sad that your connected component is smooth, you can always blow it up and make it singular. So this isn't really much of a restriction. So then the pullback map on forms is an isomorphism on Dolbeault cohomology. So in order to prove this, you have to use functoriality of all of the constructions with respect to Galois extensions and modifications. So essentially, first you pass to a Galois extension so that you can use the previous theorem. And you might have to make some modification to your skeleton. So you have to prove that everything behaves well with respect to all these constructions that you do. And that's what, so a lot of the technical details hides in there. Anyway, once you have this, then that's actually enough to compute the Dolbeault cohomology of any compact rigged smooth curve. So let's let X be a connected curve, and G is just going to be the first Betti number of the underlying topological space, which is the same as the genus of any skeleton of X. So then the Hodge diamond for weakly smooth forms. So if the boundary is empty, which means it's a proper curve, then it's exactly the same as what you think. It's 1, G, G, and 1. So this G here, by the way, this G here is, again, this is the first Betti number of the underlying topological space. Now, the relationship with like the genus of the curve X, like if it's an algebraic curve, for instance, is not so obvious because, I mean, we're not assuming that X has a semi-stable model over our field, and it can happen that after you pass to a Galois extension so that semi-stable models exist, it can happen that the first Betti number goes up because it's, I mean, you can certainly quotient by like involutions that of the skeleton. I mean, the Galois action can induce involutions of the skeleton that will turn a circle into an edge when you quotient. So this G really is the underlying topological space of X over the field it's defined over. And then again, you get the same thing if the boundary is non-empty, then H11 is 0 and H10 is G plus the number of boundary points minus 1. So I should say that Philip proved that that the Hodge diamond on the left is, so if you're working with Mumford curves and smooth forms in the sense of the Antoines, then Philip proved that you get the Hodge diamond on the left for a Mumford curve. So, and again, essentially the difference between smooth forms and, well, the difference between smooth forms and weakly smooth forms essentially is that a piecewise linear smooth function is harmonic. A harmonic function is smooth in the sense of the Antoines, if and only if there's some condition at the vertices of genus, at the points of genus greater than 0. And it's some condition that, here I can tell you, actually, well, let me tell you what it is. So relationship with smooth functions. So here's essentially what the relationship is. So if I have a point in my curve and it has an associated, so this is in the interior of the curve. So then it has some associated connected component or irreducible component, which I'll just assume is a smooth irreducible component in the special fiber of the curve. Then to any, right, and so I'm going to assume X is also in some skeleton. Right, sorry, what do I want to say? So this is a vertex of the skeleton associated to my semi-stable model. Then to any adjacent edge, I can associate the associated singular point of XS. So edge E, I get I guess this is a closed point of C. And again, remembering that edges in the skeleton correspond to singular points on the special fiber of my semi-stable model, this is just the associated point. So if I have a harmonic function, or let's say sigma, then I get slopes at each edge, outgoing slopes. at adjacent edges to X. And so this actually gives me an R divisor of degree 0, where I just take the sum, oops, there we go, sum over all edges adjacent to X of dH dTE times the associated point. So this is in pick 0 of my component tensor R. And again, it's in pick 0 because harmonicity means that the sum of these outgoing slopes is equal to 0. And so one thing essentially that Touye shows is that H is smooth in the sense of the Antoines if and only if its image in the Jacobian tensor R is equal to 0. So it's essentially that a divisor is a principal divisor. So smooth functions in the sense of the Antoines locally have the form log absolute value f. And so if you have a function of the form log absolute value f, and then you you look at the associated R divisor, then this divisor here, and this is principal by definition. Or well, I guess not by definition, but it is principal. It's in fact equal to div of some reduction of f. So the main difference is whether or not this thing, the image of this R divisor, is principal in the appropriate sense. However, if all irreducible components are rational, then the Picard group is 0. So this condition is vacuous. And for this reason, when you're working with Mumford curves, there's really no difference between the two theories. So this is something that always, that really only shows up for non-Archimedean curves with higher genus components or higher genus points. All right, so there's also a Poincaré duality statement. So if X is proper, which is the same thing under my hypotheses, it's the same thing as requiring that the boundary is empty, then integration plus Stokes' theorem in the usual way that gives you pairings that, I meant to write, okay, these pairings descend to cohomology is what I did not write in the slide, because again, the integral of an exact form is 0. So Poincaré duality is a statement that if X is proper, then the above pairings on cohomology are perfect. And this is probably what you'd expect from the previous slide, because H01 and H10 both have dimension G. And in fact, it's because of the dimensions of vector spaces that are canonically dual to each other. And this, again, is something, the way you prove this is you reduce to the case of graphs by showing that everything is compatible with integration. But pullbacks of forms from the skeleton is compatible with integration. And you use the corresponding fact for graphs. And again, Philip proved this for the smooth Dolbeault cohomology of Mumford curves as well. And for essentially the same reason as I was discussing before. All right, so I'm going to end early. I don't have much experience with timing Zoom talks like this with slides, so I appear to have prepared about 45 minutes of material. So I'm going to stop there.